You have seen these three numbers very often in process capability analysis: 1.33, 1.67, and 2.00. They appear in customer specifications, supplier quality agreements, and audit checklists across every industry. But where do these thresholds actually come from, and how do you know which one applies to your process? Hello everyone, in this video we will break down what each CPK level really means in terms of defect rates and sigma levels, so you can set targets with confidence. A quick refresher before we compare the thresholds. CPK measures how well your process fits inside the specification limits while accounting for centering. It takes the distance from the process mean to the nearest specification limit and divides it by 3 standard deviations. A higher CPK means more breathing room between your process variation and the point where parts become defective. Every threshold we discussed today is simply a statement about how much of that breathing room your customer expects. You will hear defect rates expressed as PPM, which stands for parts per million. It is simply a way of putting defect rates on a common scale. A PPM value of 63 means that out of every 1 million parts produced, you would expect about 63 to fall outside the specification limits. The lower the PPM, the fewer defects escape your process. Let's assume the process is perfectly centered between the specification limits, so both sides produce the same defect rate. So the defect rate shown will represent both sides combined. Cpk of 1.33 corresponds to a 4 sigma process. The nearest specification limit, in our case the upper specification limit, sits 4 standard deviations away from the mean, giving you a defect rate of roughly 63 parts per million on the short term. This is the most common minimum requirement in manufacturing, and for good reason. It provides a full sigma of buffer beyond a barely capable process, which absorbs small shifts in the mean before defects appear. For most general purpose characteristics, 1.33 is the accepted floor for ongoing production. Cpk of 1.67 raises the bar to 5 sigma, cutting the expected defect rate to under 1 part per million. You will see this requirement on safety, critical, or special characteristics, and it is the common expectation for new process launches in automotive under production part approval process. The logic is simple. New processes have not yet demonstrated long-term stability, and critical features cannot tolerate the risk that a modest mean shift would create at lower capability levels. Cpk of 2.00 is the definition of a 6 sigma process. The nearest specification limit is 6 standard deviations from the mean, and the short-term defect rate drops to about 2 parts per billion. But you have probably heard 6 sigma linked to a different number, 3.4 defects per million. So why the gap between 2 parts per billion and 3.4 parts per million? Because the 6 sigma concept assumes a long-term 1.5 sigma shift in the process mean. That shift turns a short-term CPK of 2 into a long-term PPK of 1.5, and it is this long-term PPK of 1.5 that produces the 3.4 defects per million figure everyone quotes. So let's put all 3 levels side by side. 1.33 gives you 63 defects per million. 1.67 takes you below 1 per million. 2.00 pushes into parts per billion territory, or 3.4 per million once you account for the long-term shift. So which target should you use? Match the requirement to the consequence of failure. General characteristics in stable production, 1.33. Critical characteristics, new launches, or anything tied to safety and regulation, 1.67. 6 sigma programs and processes where downstream failure cost is extreme, 2.00. If you want to calculate CPK and PPK on your own data, SigmaDesk includes a web-based capability analysis module with no installation required. Just paste your dataset and see all the metrics immediately, including exactly what defect rate is expected from your process based on your CPK and PPK values. The link is in the description. If this video helped you, do not forget to like the video, which really helps. Also subscribe for more practical quality engineering content, and I will see you in the next one.